Hello everyone and welcome to chapter Mechanical Wave of PHY534. In today's session, we will explore the topic of mechanical wave, focusing on their types, wave functions, and transverse speed. Here is the subtopics. Types of wave. Here we have three main types of wave: mechanical wave, electromagnetic wave, and matter wave. So, for the mechanical wave, are most familiar because we encounter them almost constantly. The common examples include the water wave, sound wave, and seismic wave. All these waves have two central features. They are governed by Newton's law and they can exist only within a material medium. Next is the electromagnetic wave. These waves are less familiar, but you use them constantly. The common examples include visible and ultraviolet light, radio and television wave, microwave, X-ray, and radar wave. These waves require no material medium to exist. Next is the matter wave. Matter wave is related with the materials or the particles inside the materials. Although these waves are commonly used in modern technology, they are probably very unfamiliar with us. These waves are associated with the electron, proton, and other fundamental particles, and even atoms and molecules. Because we commonly think of these particles as constituting matter, such waves are called matter wave. Next, we focus by narrowing down the types of the mechanical wave. Okay, students, let's begin with the types of the mechanical wave. Mechanical waves require a medium to travel through. There are two primary types of the mechanical wave. First is the transverse wave. Next, the second one is the longitudinal wave. For the mechanical wave, in the transverse wave, the particles of the medium move perpendicularly to the directions of the wave. Here, for examples. An example is a wave on a stretched string. If we look at the single point on the string, it moves up and down as the waves travel horizontally along the string. In contrast, a longitudinal wave involves particles that oscillate parallel to the wave directions of travel. A good example for the longitudinal wave is a sound wave in air, where the air molecule move back and forth along the directions of the wave due to a vibrating piston of source, like in this picture. So, as a conclusion, both transverse and longitudinal wave are known as traveling wave because they carry energy from one point to another, from one point to another, and here from one point to another. Okay, this is the examples of the longitudinal wave, and here is the examples for the transverse wave. We consider here only an idle string which no friction like forces within the string causes the wave to die out as it travels along the string. In addition, we assume that the string is so long that we need to consider a wave rebounding from the end. Here, both of transverse wave and longitudinal wave are said to be traveling wave because they are both travel from one point to another. Next part is the wave function. Okay, students, to describe how a wave behaves, we use a wave function. This function gives us the shape of the wave and tells us how that shape changes over time and space. In other words, the wave functions allow us to calculate the displacement of any point on the string at any given time. Mathematically, the wave function is often written as y in the function of x t equal to ym, or we can set as an amplitude, sine or cosine in the function of kx plus or minus omega t. Here, x represent as a position while t is represent time. This equation help us visualize the entire wave and track its motion as it moves along the medium. Here is the 5 snapshots of a string wave traveling in the positive directions of x-axis. The amplitude Ym is indicated here. A typical wavelength, lambda measured from an arbitrary position x1, is also indicated. The amplitude of wave, such in the previous figure, it is the magnitude of the maximum displacements of the element from their equilibrium position as the wave passes through them. Because Ym is a magnitude, it is always positive quantity, even if it measured downward instead of upward as drawn in the previous figure, while the phase of the wave is the arguments of kx minus or plus omega t. As the wave sweeps through a string element at a particular position x, the phase changes linearly with time. Also, we have wavelength of wave. It's the distance between the repetitions of the shape of the wave, or wave shape. Next is the angular wave numbers with the symbol k. K equal to 2 pi over lambda. K or angular wave number of the wave. Its SI unit is the radian per meter. An element of the string at x at this time t has the same position y as an element located at x minus vt at a time t equal to 0. So in general, based on these equations, if the pulse travels to the left, the transverse position of the elements of the string are described by this equation. Waveform is the wave function y in the function of x at a fixed t, and it is a curve representing the geometric shape of the pulse at that time. If the y versus x plots, we can get the wavelength here. The wavelength of wave is the distance between the adjacent crest or adjacent trough. While is a plot y versus t, we can get t period. The period t of wave is the time interval required for the element to complete one cycle of its oscillation for the wave to travel one wavelength. Again, for the wave to travel one wavelength. Okay, students, next we have phase constant. Phase constant phi in the wave function is here. So kx can be plus minus omega t, and also here can be plus minus phi, phase constant. The value of phi or phase constant can be chosen so that the function gives some other displacement and slope at x equal to 0 when t equal to 0. Here you can refer the examples and referring the graph here. Here, for a wave traveling to the right, the wave function is here. Y equal to A. A can be written as A amplitude or Ym, sign in the functions of the kx minus omega t plus phi. Next part is the transverse speed, which is referred to the speed of element of wave. Okay students, next let's look at the transverse speed. This refers to how fast a particular point on the string moves up and down. But here, this speed is not the speed at which the wave travels along the string, but this speed is referring to the vertical speed of a single particle. This is due to the wave motion. By understanding the transverse speed, it is very important for analyzing the energy and intensity of wave in different scenarios. Here we have equations V, or the speed in this component y, okay, which is we set as the vertical speed equal to dy per dt, where x is constant. Here the equations for the speed. Okay, but also we can also calculate the accelerations with the component y, okay, which is acceleration in the component y equal to dv per dt, where x is constant, so this is the equation. And here we also can get the equation, the maxima of the transverse speed and acceleration. The maxima for the transverse speed and acceleration are given by this equation, which are the same as those in the simple harmonic motion. Okay class, and all my students, that's all for this part of chapter mechanical wave. In summary, we have looked at the two types of mechanical wave, learned how to describe them using a wave function, and discussed the concept of transverse speed. Thank you for tuning in.